In this installment, we are going to look at some applications of linear momentum. The first one of these is a very common one. We have a gun, and a word that you may not be familiar with is recoil. To recoil means to move back from, to move away from. So what we have in the first image here is a gun with a bullet inside, like so. And so we have our system, which is the gun bullet system. And afterward, after the gun is fired, we have, again, the gun bullet system, like so, with the bullet going this way and the gun recoils. So we have an initial momentum, which is equal to 0, and that must be equal to the momentum afterward. Afterward, we have the momentum of the gun and the momentum of the bullet. So then we can see that the momentum of the gun must be equal and opposite to the momentum of the bullet. So the mass of the gun is equal and opposite of the mass of the bullet times the velocity of the bullet. Mass of the gun, velocity of the gun. Left that out on that side. So if we measured the velocity of the bullet, we could find out the velocity of the gun. And so solving for the velocity of the gun, we would get negative mb over mg times vb. So we have this ratio of the bullet to the gun. Now the bullet is very, very small compared to the mass of the gun. So that means this fraction, this ratio of the masses will be a small number. So you take a small number like, say, 0.1 and multiply it times the velocity of the bullet, then the gun would have a much smaller velocity than the bullet. And notice then that the ratio of that velocity of the gun is inversely proportional to the ratio of the masses. So that's how we can analyze a gun in the case of explosions and conservation of momentum. Now we can look at water hoses. So we could have a fire person like so, and they are holding a fire hose like so. And what they have inside that hose is water. So the system in this case is the hose and water and the person. So when they take the hose and open it up, is the water now starts to come out. And so we have a change in velocity of the water in this direction, which must result then in a change in velocity of the person and the hose. And the momentum change on the part of the water is going to be equal and opposite to the change in momentum of the person in the hose. And so this is why the larger the hose volume is, or the higher the velocity, the more difficult it is for a person to hold it. And we might end up adding additional fire people to hold it in place. It could be that there's such a change in momentum of the water that a person cannot hold that hose. It would actually just fly around with them. And so, of course, the change in momentum of the water would be mass of the water times the change in velocity of the water. And the change in momentum of the hose would be the mass of the hose person times the velocity of the hose person. And we could do the same kind of accounting with water and air hoses. Next, we could look at some elementary rocketry. And the elementary rocketry will break down into two different types. The first one will be a balloon. Because from our very early ages, we would play with balloons and we could release them and they would behave like rockets. So in the beginning, we have a small little balloon like this, and we add air to it. And it expands. And all the while it's expanding, the balloon is pushing inward. And the air is pushing outward. Plus, there is also, so this is the rubber, there is also an inward force from the atmosphere. So we have a force outward that we are blowing to hold it in place, and then there is a force outward, or force inward of the rubber trying to squeeze it, and as well as the atmosphere pushing outward. So at any moment in time, the force of the atmosphere and the rubber will be equal and opposite to the air pressure we've put inside. And so we hold that air in there, and then we release that. We no longer hold that balloon closed, and of course what happens then is we get air rushing outward. So the change in momentum of the air is going to be equal and opposite to the change in momentum of the balloon and its air inside. And of course, that change in momentum of the air is the mass times its change in velocity, and the change in momentum of the balloon is the mass times its change in velocity. And so that's the basic principle there of a balloon. Now, if we were to look at a simple rocket, like a toy-type rocket, it's very similar. It's similar to, but different from a balloon. So we have some kind of fuel or mass inside the chamber of the rocket. And so in the beginning, we have the momentum of the rocket and the propellant. We would call it the propellant. And so our initial momentum is 0. And afterward, we have the momentum of the rocket plus the momentum of the propellant. And so then the momentum of the rocket will be equal and opposite to the momentum of the propellant. And the change in momentum of the rocket will be equal and opposite to the change in momentum of the propellant. And so the propellant starts to leave. It starts to leave like so, and we get a change in momentum. And what is not obvious about this is what's going on with the individual molecules. So if we zoom in on a very small scale, these molecules here are moving around, and they are exerting a force on the rocket, and the rock is exerting a force backward. So the gas molecule exerts a force on the rocket, a force times a period of time, and that's of the gas molecule on the rocket, and the rocket exerts a force over a period of time on the gas molecule. And of course, we know the time that they're interacting with each other are equal and opposite, so the forces are equal and opposite. So what's happening is the gas molecules are exerting a force on the rocket's exerting a force on those molecules, and the result of that is it allows the gas to escape. And that escape, the accelerations of those particles, are equal and opposite to the mass times acceleration of the particles are equal and opposite to the mass times the acceleration of the rocket. But ultimately, it's all about a conservation of momentum. Now, what is truly exciting now is some of the new technology